Okay, so in this video, we are going to look at the mean value theorem. So here's a statement. So you let f of x be a continuous function on the closed and bounded interval ab. So here we assume that a and b are real numbers, where a is less than b. And we also assume that f of x is differentiable on the open interval ab. So the derivative of f at any point between a and b exists. Here's the conclusion. Then, and that's the mean value theorem, there exists at least one point C in the open interval AB such that the derivative of the function at C equals f of b minus f of a over b minus a. Now if you think of what this is geometrically, this is the total change in y of the function f over the interval ab. F of b is the final value of the function minus f of a, the initial value. So that's the total change in y over the total change in x, b minus a. So this is the average slope of the function. Total change in y over the interval over total change in x. And so the mean value theorem says that there has to be at least one point between a and b where the derivative of the function at the point c equals the average derivative, the average slope of the function over the interval ab. And that is the mean value theorem. Now if you want, you can rewrite the conclusion in the following way. You can multiply across by b minus a, and so you'll see that f of b minus f of a the total change in y of the function over the interval from x equals a to x equals b is equal to the derivative of the function at some point between a and b times the change in x, b minus a. And that's a different way of looking at the mean value theorem. So the total change in y of the function, f of b minus f of a, will equal the derivative of the function at some point in between a and b times the change in x, b minus a. And the proof of this result will be surprisingly easy since we already have Rolle's theorem. This will be a direct consequence of Rolle's theorem. Before we prove the result, let's look at why this is very intuitive geometrically, and also see that there are possibly several points in between a and b where the derivative of f at the point is the average slope of the function. So imagine that the graph would look something like this. Just for simplicity of the picture, I'll assume that f takes on positive values. So this is the point A. This is the point f of a, the y value of the function. Assume this is now point B, and say this is f of b. And now the function goes from af of a to bf of b. The function was assumed to be continuous. There are no break in the function. And it was also assumed to be differentiable. So everywhere between a and b the derivative exists. So the tangent line to the function exists. So the function will be smooth. You can draw any function you want. I'll just draw it increasing like this. Or maybe concave down. So suppose that that's the graph of y equals f of x on the interval a to b. Let's look at this quantity here, right? If you look, f of b minus f of a is the total change in y. B minus a is the total change in x. Let me connect the point AF of a with the point BF of b with a line segment. And ask quite simply, what is the slope of this line? Right, if you notice, this is the change in y, this is the change in x. So, We'll call this delta y, the change in y. As always, it is the greater value minus the smaller value, so it's just f of b minus f of a. So you see f of b minus f of a is the total change in y of the function. And if you look at the change in x, delta x, well, this is a change along the x direction, the x-axis. So it is the larger x value minus the smaller x value, so it is just b minus a. And so you see f of b minus f of a over b minus a is just delta y over delta x. So it's the slope of this line segment connecting points AF of A with point B F of B. So the slope of this line is equal to delta y over delta x. And as we have just found, this is the right-hand side of the equality in the mean value theorem. F of b minus f of a over b minus a. And now let's look at the left-hand side. The result says that there must exist at least one point between a and b where the derivative of the function at that point equals the slope of this line. Well, imagine looking at the tangent line, starting at AF of A, and gradually moving the point of tangency along. And look at the tangent line evolving. So it may start something like this, and then gradually as you move to the right, if you stop there, you see that the tangent line is parallel to this line, and if lines are parallel, they have the same slope. So the slope of the tangent line at this point, which is f prime of c, would be equal to the slope of this line, which is f of b minus f of a over b minus a. So here's your value of c. And you can see if you draw the tangent line to the function at this point, if you choose the point C just right, the tangent line is parallel to this line, therefore they have the same slope. But the slope of this line, by definition, well, this is the slope of the tangent line to the function at the point x equals c. By definition of the derivative, it is the slope of the tangent line at the value of x. And so you see, this is how you can think of the mean value theorem very geometrically, very intuitively. F of b minus f of a over b minus a, being the total change in y over total change in x, is simply the slope of the function passing through the points a f of a, b f of b. And you can see from the picture, as you move the tangent line, that there will be at least one point where the tangent line and this line are parallel, and lines are parallel if they have the same slope. Therefore, the derivative of f at c, being the slope of the tangent line at x equals c, must be equal to the slope of this line, which is f of b minus f of a over b minus a. And that is intuitively what the mean value theorem says. Let's draw one more picture to see that the point C is not necessarily unique. And I'll draw a really rough sketch here. I won't draw the axes. Suppose this is point A, f of a, point B, f of b, and the function may look something like this. Then, draw the line passing through the 2 points. And we ask, at which point on the function will the tangent line be parallel to this line? And this will give you a value of c. Well, if you look roughly here and draw the tangent line, it is parallel to this line. So this would be a value of c. This is, let me just draw the x-axis. So this would be one value of c, where f prime of c equals f of b minus f of a over b minus a. But if you look, if you keep going, there's also this point. If you draw the tangent line at this point, it also looks parallel to this line. And so the slope of this line equals the slope of this line, which equals the slope of this line. And so we have here a second value of c that satisfies the conclusion of the mean value theorem. There are 2 points, 2 values of x, where the tangent line is parallel to the line connecting the point AF of A, BF of B. And so f prime at this point equals f prime at this point, which equals the slope of this line, which is f of b minus f of a over b minus a. And I could draw a more complicated curves going up and down more several times, and you'd have even more points where the tangent line at the point is parallel to the line connecting the initial point and terminal point of our graph. So that is the geometric intuition of the mean value theorem. Let us now prove it. And the proof will be a direct consequence of Rolle's theorem. And as you will see, it is quite short. So here's the proof. Now think of finding the equation of the line passing through the points a f of a, b f of b. So let us find the equation of this line. All we need is the slope, as we have just said. The slope of this line was the change in y over the change in x, which is simply f of b minus f of a, total change in y, over total change in x, b minus a. And now, let's just check that the equation of this line is, quite simply, y equals f of a plus the slope of the line, so f of b minus f of a over b minus a, times x minus a. Let's just check this. What is the value of our function at x equals a? If you plug in x equals a, here you have a minus a, which is 0. This term is 0. And the y value is f of a. So check, our line passes through this point. And what is the slope of our line? Well, that's the multiple of x, right? So if you look, this term multiplies x. So this is the slope of our line, which is the slope of this line. And so what we have found here is the equation of the line passing through the points AF of A, BF of B. And now from this, we're going to construct a new function, simply the original function f of x minus this function. We can call this function, say, h of x. So we let the new function h of x be the original function f of x minus the equation of the line passing through the points AF of A, BF of B. So I have minus f of a minus all this, so minus f of b minus f of a over b minus a times x minus a. And so we have now this function. And if you look at it, we only took the function f and we subtracted the equation of the line passing through these 2 points. Now let's ask, does this function satisfy the assumptions of Rolle's theorem? Well, f of x is continuous on the interval from a to b. this is a line which is also continuous, so the difference of two continuous functions will also be continuous. So check. Well, the function f was assumed to be differentiable on the open interval ab. This is a straight line, also is differentiable. The difference of differentiable functions is also differentiable. So our function is also differentiable on the open interval ab. The only assumption that we have to verify now is that h of a is 0 and h of b is 0. Well, let's evaluate h at these 2 points. H of a equals f of a minus f of a, that's 0. And plug in here x equals a, you get a minus a 0. This term is 0. This term is 0. Clearly, h of a equals 0. What about h of b? Our function at the right-hand point? Well, we'll have f of b minus f of a minus, and if you replace x by b, you have b minus a over b minus a. This cancels, and you'll be left with the numerator only of your fraction, which is f of b minus f of a. But if you subtract, you'll get f of b minus f of b. They cancel. Negative f of a, negative f of a, so plus f of a. These two will also cancel, and you're left with 0. So you see that this function h of x satisfies the 3 assumptions of Rowe's theorem. Well, so now we can simply quote the conclusion of Rowe's theorem to the function h. What is the conclusion of Rowe's theorem? Rowe's theorem said, if a function satisfies the assumptions, then there exists a point, at least one, C in the open interval AB, such that, if you remember, the derivative of the function at the point C is equal to 0. So h prime of C is equal to 0. Well, let's compute now, and this is what we get from Rowe's theorem. Because the function h satisfies all assumptions of Rowe's theorem, there must exist at least one point C in the open interval AB where the derivative of our function at C is equal to 0. Well, let's differentiate h and then see what h prime of C equals 0 gives us. So h prime of x, we are differentiating. This would be equal to, well, the derivative of f of x, this is f prime of x, minus the derivative of a constant, right? A is a fixed value of x. This is a constant term. The derivative of a constant is 0. This is gone. And if you think of it, this is a constant multiple times this function. So the derivative of this will simply be the constant multiple, so minus f of b minus f of a over b minus a times the derivative of x minus a. The derivative of x is 1. The derivative of a is 0, as a is a constant. And so all we have is the derivative of this constant times this is the constant multiple times the derivative of x minus a, which is simply 1. And this is the derivative of our function h. We know that h prime at C is equal to 0. So let us replace. So h prime of C is equal to f prime of C minus, there is no x here, this is a constant term, so it's just f of b minus f of a over b minus a. And we know that the point C coming from Rowe's theorem was a point where the derivative of the function h at C is equal to 0. And now look at this equality, send this term on the other side, and what have we just found? We have found a point C where the derivative of the function at C is equal to, right, when you send this on the other side, the negative becomes a positive, so quite simply f of b minus f of a over b minus a. And this was the desired conclusion of the mean value theorem, that there exists a point C inside of AB where the derivative of the function at this point equals the average slope of the function over the interval, total change in y over total change in x. And this completes our proof. In our next video, we will consider a few examples of the mean value theorem.